Hello, everyone. Good morning, afternoon, or evening. Dear authors and invited guests, welcome to Technical Session 6B. My name is Alesha Mullah, and this session will be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, ICICT, London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held on the 25th of February in London, and the physical event was held on 24th of February in London, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you will enjoy the knowledgeable and interactive sessions through the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentation and 3 minutes for question and answers. On the 10-minute mark, I will raise a gentle reminder. There is another request to all the participants. Please stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in the chat box. Just before we start the session, I would like to introduce you all to the chairs for this session. Our first chair for today is Dr. Anubha Jain. Dr. Anubha Jain is working as a director, School of Computer Science and ITIIS, deemed to be university in Jaipur. An academician for the last 23 years, she has actively contributed in teaching, industry, and research and development. Her research interests include soft computing, computational studies, IoT, and software engineering. She is the author of 9 books and has published a number of papers at national as well as international level. Dr. Jain, I request you to please say a few words.
Yeah, good morning, everybody. I hope everybody is doing good, and my best wishes and congratulations to all the conference organizers. Thank you for inviting me and others as for this conference, and it's a lovely platform to share your research ideas. And I'm hoping to see some great research work during the conference. All the best to all the participants. Thank you.
Thank you, Dr. Jain. Our next chair for today is Noura Muhammad Sani. Noura Muhammad Sani is a lecturer in the Department of Computer Science at the Federal Polytechnic, Koltungo, Gombe State in Nigeria. He specializes in artificial intelligence, machine learning, and deep learning, and is actively involved in teaching and academic development in emerging computing technologies. Mr. Sani, I request you to say a few words.
Good morning, good evening, good afternoon, everyone, wherever you are from. I'm really excited to see myself in this session as a session chair alongside with my colleague, Dr. Anubha Jain. So I wish all the participants successful presentation, and I pray for the success of the presentation. Thank you so much.
Thank you, sir. We can now begin with our first paper for today. Our first presenter is Maximilian Deharde, who will be presenting his paper on development of a mobile outdoor diminished reality application for real-time visualization of urban greening projects. You may now begin your presentation.
Thank you. I'll send a request for presentation rights. Yeah.
I believe you can start your presentation now.
Yep. That should work. I assume everybody can see the screen now. All right, thank you very much for the introduction. As you already mentioned the title, I'll skip right to our motivation for the paper. So we can constitute that climate change in general results in harsher living conditions for city dwellers, especially due to heat buildup. Heat buildup being an issue specifically if there's large areas within the city that are asphalted without greenery. This heat buildup causes issues specifically for weaker people and causes higher mortality rates in very, very hot summers. Urban greenery is a method to counteract this heat buildup. So additional city trees, additional green spaces, and overgrown building facades can mitigate this, amongst other benefits. while planning these greenery projects, augmented reality visualizations can be used to communicate them with locals prior to the actual execution. So you can see on the right an image of a greenery project that hasn't been actually executed yet, that is still in planning on a static image. And this static image could be converted into an augmented reality visualization where the actual result is more believable, more immersive, more interesting, and more useful for communication. There, however, is an issue with augmented reality visualization, specifically in urban settings. So AR visualizations only work well where the area where the virtual content is to be placed is empty. So as soon as real objects and virtual objects share the same space, implausible images are created and the visualization loses its value. Specifically in urban scenarios, space is commonly occupied just because of high development densities. So there's cars, there's people, specifically where urban greenery, for instance, could be visualized. And to mitigate this issue again, diminished reality can be used. Diminished reality is a technology that allows the removal of real objects in real time, mostly within an augmented reality application. To accomplish diminished reality, there are four central steps. And the four steps are first, the objects that should be removed need to be detected, seen, or shown on the image on the left. In this case, a bike within the city should be removed. It needs to be detected, step one. Step two, once the object is detected, object instances must be tracked in every single frame afterwards. Step three, the background that is occluded by the object needs to be generated. So in this case, the house and the part of the street that are occluded by the bike. And step four, the generated background must be overlaid to hide the actual object instance. And once we accomplish these four steps, the object seems as though it doesn't exist, even though in the camera image of the mobile application, in theory, it still is there. Two of these four steps are particularly computationally expensive, and this is always an issue with diminished reality methods because they require real time. As soon as the diminished reality method no longer sustains real-time capability, it doesn't work anymore as an enhancement of the visualization. So two of these steps are particularly computationally expensive and therefore threaten the real-time capability, and that is detection and background generation. Both of those are very expensive. The tracking and the overlay are fairly cheap. Detection these days usually is done by neural networks, just because detection-based neural networks have gotten so good over the years. And the background generation is a bit more diverse. There's more options there. And we focused in our research specifically on photogrammetry. So an example is shown from a different research group on the right, where photos of the actual background that should be overlaid over real objects is pre-generated. The photos are then used to make to create 3D point clouds. The 3D point clouds are then used to make 3D background models that can then be rendered specifically within the mask of the object that are to be removed. So on the right, you can see a person and a building. The green mask is the area that needs to be overlaid, and then the 3D model is rendered specifically within those masks. However, creation of these 3D background models is very expensive, as in it's labor expensive, it takes a long time to accomplish, and it's labor intensive because the photos need to be taken and so on. Our approach uses a similar methodology, but tries to avoid these problems. Specifically, our idea for urban scenarios for urban greenery was to use the freely available 3D models of entire cities that already are available. So don't need to be generated specifically for our tasks, but already exist. You can see on the right an image of the 3D model of the city of Berlin that is freely downloadable, freely usable. So the idea was to use this 3D model instead of pre-generated ones, specifically for diminished reality tasks, and therefore would add a general availability of diminished reality functionality for the entire city of Berlin. Again, this has a couple of benefits. For one, the low computational requirements, because rendering of 3D models is fairly cheap compared to other methods of background generation for diminished reality, and the ease of use for the mobile application because many things can be automated. There's two main challenges. One of them was the precise placement of the 3D models to match the real world surroundings, right? So the 3D model needs to be exactly matching the surroundings of the actual device at runtime. And the data transfer of the 3D model to the mobile device needs to be appropriately accounted for. Our proposed architecture for the mobile application and the backend that supports it, fairly straightforward setup. We propose a mobile outdoor diminished reality application that implements a user interface and has three main components: the augmented reality component that visualizes urban greenery, the geopositioning component that ensures that the device location is known at all time and device orientation is known at all time, to then use this information to place the 3D models of the city appropriately so that it matches the environment. And then the diminished reality component that renders these 3D city model parts specifically within the areas of the screen where objects are detected. The communication layer then handles communication between data storage and client. So whenever a chunk of the city is needed, it can be transferred. Our diminished reality component is built as follows. We use a neural network for detection tasks. The user manually selects objects that are detected, pardon me, that are detected within the screen. The tracking is done via new detection results and old detection results, comparing them and checking if there's overlap. Within the access line bounding boxes, the 3D city model is rendered, and then the image is composed of a real camera image and the 3D model part. We implemented a prototype using Unity as a development environment, AR Foundation as an AR framework, and Centis as an inference library to run detection tasks with our neural network. The network or the model we used was YOLO v4 Tiny. And to determine the device location, we used the Google Geospatial API that works very well in urban environments specifically. To our key results, I'd like to first describe the three images that you can see to give you an idea of how it looks. Number one on the left is the unmodified camera image of the prototype. So you can see a real bike at the corner of the street. Image two in the middle is the AR enhanced camera image. So we enhanced the camera image with AR content, some generic urban greenery that in this case takes up the same space as the bike, which is exactly our issue that we want to solve, because the fact that they take up the same space causes visualization issues. And the image on the right then is the simultaneously enhanced and diminished camera image. So the bike was detected, the bike was selected by the user, and then within the access line bounding box of the bike, the 3D city model is rendered. So you can see the markings on the street that continue from real part of the camera image into the 3D model. To summarize, the implementation of the main AR functions and DR functions was successful. We can place the 3D city model very accurately according to our localization results from the Google API. The detection model YOLO v4 Tiny was sufficient for a task, although sometimes also caused issues due to instability. But fundamentally, despite everything working as planned, the visual results were not as we had hoped, as you can see on the right, because you can definitely tell the difference between real and virtual part, or yeah, synthetic part of the camera image. What were the key issues that we faced? Number one, the resolution of the city model is insufficient. Um, Number two, the angle of the imagery, because it's an aerial image, caused objects to bleed into one another. You can see that on the right. The tree bleeds into the building facade. The color values were mismatched because of ambient lighting mismatch, current and time of recording of the images. And the mesh contained real-world objects that they themselves caused visualization issues. So the car visible on the left, that is part of this 3D city model, caused issues just like a real car. To end the presentation, we start out with the fact that urban greenery projects that have very specific locations should still and can still use this pre-generation of 3D meshes to use as background imagery. It's still a reasonable approach. However, for generic, all-purpose, non-predetermined locations, different approaches need to be used. And specifically imaging painting with appropriate neural networks is probably a reasonable approach that should be pursued in the future. That is it from me for now. Thank you very much for listening.
Hello. Am I audible?
Yeah, I can hear you.
It was a very good presentation, Max Millet. So
Thanks.
I have a question that how would your application lead to sustainability?
I mean, sustainability is somewhat
Like you are
outside of the scope,
talking about
right?
climate change and everything. So
Yeah.
somewhere around the corner, you are talking about building a green model, right?
So the idea would be that so communication is always an issue when it comes to changing the landscape around people, around individuals, right? If suddenly somebody says, "Hey, we're going to build something right next door to you," maybe I don't like that, or I'm scared, or I have concerns, and communication is central to essentially remedying these issues. So the better the visualization is, the better I can communicate things. And static visualizations are okay, and dynamic ones are just a step up, right? So the idea would be that the fact that you can visualize things better, make people accept changes in their environments more, um, leads to additional greenery projects that actually get executed, and then maybe as a last step, that increases sustainability, prevents issues with climate change, heat buildup within cities, right?
Okay, and in the urban landscapes, usually there would be some construction or other going on, right? So
Right.
won't the model keep on changing?
That is essentially the issue as well, right? The fact that the snapshot within the 3D model is just that, is just a snapshot. Um, doesn't account for changes. So the only way that you can use these 3D models, it seems, is that it's a specific location for a specific time, and you can very much curate the result. Um, as you said, if things change, it won't work as well anymore, and there'll be other issues. Yeah.
Okay, thank you from my side.
I have one question.
Thanks. Yeah.
Regarding you talk about the visualization was not realistic enough. So in this regard, how can this realism of diminished reality visualization be improved, especially with respect to the quality of this DCT model? How can it be improved?
So in theory, the 3D city model could be made better, as in higher resolution. That is one option. The second option would be specifically color matching. I think that's a big issue that makes it non-believable. The fact that the image shown here is color-wise so different than the actual ambient lighting. So that would be one approach. But fundamentally, I think all of these are just patchwork solutions, and I think at the core, the approach needs to be changed. I think the usage of image generation at runtime using the real camera image as patches for creating the actual background without observing it is probably the most realistic way to go about it. Yeah.
Thank you so much.
Thanks.
Thank you. Our next presentation will be by Gennady Lukyanov, who will be presenting their paper on experimental study of the behavior of a silicon wafer with self-affine surface relief during periodic heating and cooling. You may now begin.
Just a moment. So, device with surface having a regular relief constructed according to the certain law has been known for a long time. Such devices are widely used, for example, in optics. So it's Fresnel lenses, diffraction gratings, etc. Previously, we examined the modeling and simulation of a silicon wafer with a self-similar surface pattern of circular grooves. It was expected that when exposed to an electric field, such a semiconductor wafer would become electrical, similar to devices such as a MOSFET transistor, which operate on a principal budget of ability of semiconductors to transition from electrically neutral state to an electrically charged one. So you can see here this semiconductor place with a self-similar relief. The basis of this is electrical polarization. The emergence of free electrons or free charges in an electric field. The arrangement of the grooves results in the uneven concentration, you can see here, of electrical charges on the surface of the plate. It is energetically more favorable for charges to be located where the grooves are located. Since the concentration of electric charges in a semiconductor strongly depends on temperature, it is interesting to see how such a surface formed on a semiconductor plate behaves when the temperature changes. Therefore, it was interesting to study the behavior of an object such as a wafer with a self-affine ring pattern on its surface under the influence of temperature field. If a heat flow directed, For this experiment, periodic heating and cooling using a Peltier battery was applied. The reaction of the plate surface was recorded using a thermal imaging device. the temperature field of the surface was measured. So you can see here on our setup the Peltier element, and here on another photo our plate with self-affine relief on the Peltier element. The current polarity switching circuit is shown on the slide, and one polarity of current, the resonator, was cooled and the other heated. The temperature distribution was measured using a Testo 890 thermal imager. The thermal imager was installed so that the focal plane of its length was perpendicular to the normal from the resonator surface. And yes, here you can see the examples of thermograms obtained by periodical heating and cooling. The radiation is heated body is described by Planck's law. You can see here. Planck's radiation law applies to the so-called black body. The fundamental properties of black body are that, firstly, it absorbs all incident radiation, and secondly, it always emits more energy than any other body at the same temperature. A model of black body is a cavity with a hole or some kind of depression of the surface or a groove. When, for example, a beam, you can see here, of light enters the hole in the cavity, it is repeatedly reflected and absorbed by the walls of the cavity, and the probability that it will leave the cavity through the hole is extremely small. However, these models do not fully possess the properties of a black body, the same energy absorption as a black body, and the difference between a real body and black body is characterized by a so-called absorption coefficient. According to Kirchhoff's law for a body in thermal equilibrium, its emissivity is equal to its absorptivity at the same temperature. Using the Testo thermal imager, the temperature field of the resonator surface was measured during heating and cooling. You can see here the result. Pardon. Heating and cooling were controlled using a Peltier battery. The result obtained, namely the temperature change of the central part of the resonator, with relief, the temperature of its peripheral part, and the temperature of the Peltier element over time are shown in the graph. The graph shows a significant difference between the measurement temperature of the central relief TR and peripheral smooth TW parts of the resonator, even though the temperature are equal. This is explained by the different absorption coefficient of the parts. Absorption in the central part is significantly higher. Why did the temperature measurements of object in close thermal contact with the same surface differ because the emissivity of this object, which according to Kirchhoff's law are considered equal to the absorption coefficient, differ. Knowing the emissivity factor of the Peltier element surface, we can determine the emissivity factor of the resonator for the central part with relief and the peripheral part without relief, polished silicon. So the emissivity factor for the Peltier element is equal 0.8. Based on the Stefan-Boltzmann's law, the emission factor for the central part are equal. You can see here absorption of central part changed equal to the part of Peltier element. So this means that the emissivity factor on the grooves portion of the resonator surface is significantly higher than the smooth peripheral portion. It is evident from the graphs that a sharp decrease of the emissivity occurs at moments of a rapid change in the direction of temperature change. This can be explained by the fact that the rapid change of the concentration of charge carriers in the grooves region should also occur. The concentration of the charge carriers in the core part of the resonator with sharp temperature changes is higher than in its peripheral regions, therefore, due to additional absorption by change carriers. The emissivity coefficient of radiation increases here. It is known that semiconductors have a very strong exponential dependence of the concentration of charge carriers on temperature. Therefore, the proximity of the apparent temperature of the central part of the resonator to the temperature of the Peltier battery is explained by a sharp increase in the concentration of electrons. The concentrations near the grooves and additional absorption of light by these electrons by Zeiger.
Excuse me, I'm so sorry to interrupt. You have 1 minute left.
10 seconds. Okay. Entschuldigung. Excuse me. Also, when the resonator is heated, firstly, it leads to an increase to the concentration of charge carriers. Secondly, when heated, a temperature difference arises between the lower plane of the resonator, which is contact with the heat source, under the influence of temperature difference and heat flow, electrons diffuse from the lower surface of the resonator heated by a Peltier element to its upper surface. And references. Thank you very much. I'm ready.
Thank you so much for this wonderful presentation. My question here is that, can this approach be applied to other semiconductor materials besides silicon? Like the most common semiconductor is silicon, but we have other modern electronic semiconductors such as gallium nitride and silicon carbide. Can this approach be applied to this type of semiconductors?
I think time is over.
silicon is widely
Please
used.
come to the conclusion slide.
Pardon.
Yes.
Silicon is widely used in electronics. And they have this element to protect from so-called electronic smoke, like Wi-Fi, mobile nets, but it's our next publication. So, thank you very much.
Thank you. Our next presentation for today is by Yusua Hirschkin, who will be presenting his paper on the development of an intelligent assistant for hydraulic system maintenance and assembly. You may now begin.
Okay, good morning, everyone. Okay. I hope you can all hear me and see the presentation. Is that correct?
Yes, we can.
Okay, thank you. Then thank you very much for the introduction. And good morning, everyone. My name is Josa Höfgen. I'm with the Chair of Automation and Information Systems of the Technical University of Munich. And as introduced, I'm going to present on the development of an intelligent assistant for hydraulic system maintenance and assembly. So let's have a brief look at the agenda. So I will be mainly focusing on our contribution in the framework architecture and the insights gained from the evaluation results. And with that being said, let's start with a short motivation and our main research questions. So in order to understand the kind of problem we are trying to solve, let's look at a concrete use case and application example. In this example, a maintenance worker is somewhat roughly familiar with the general maintenance procedure and just requires some selective information how to proceed in a specific step. So let's assume we have, for instance, unscrewed a little cap of our oil filler tank. And so we ask our system, okay, I have removed this little cap, but what is next in our procedure? We assume some sort of large language model and knowledge graph-based system that has structured information of this maintenance procedure available and can thus answer, okay, I see you are now in step 5 of this specific procedure, and the next step would be to check the oil filling level, with of course the goal that the worker can continue its maintenance procedure. So our main objectives here are to retrieve a precise reference to a concrete step in a maintenance or assembly instruction, and from there on move deterministically forward for the search of the next step. So industrial hydraulic systems have a few characteristics that make them particularly interesting to study them in the context of information systems. They are typically of high structural complexity, and also the routines are typically of high procedural complexity. And alongside comes, of course, safety concerns, which are due to the high pressure, for instance. And usually all this information, all the maintenance, assembly steps, they're usually very vast guidance material, documents existing for them, which makes it hard to access very specific information when performing an action. So this leads us to the first research question: is how can the identification of a required task in a specific maintenance or assembly routine be supported? And how can various types of supporting information, such as warning labels for safety concerns or additional information, be delivered for context-aware instructions? Now, for the state of the art, we mainly looked on intelligent assistance for maintenance and assembly, where there's notable work done in manufacturing and process engineering as well for robotics. Notably, there exists also prior work on knowledge graphs for hydraulic systems. And since we use an LLM-based knowledge graph-enhanced retrieval augmented generation system, we looked at several techniques to graph traversal. and also different kind of existing applications in automotive, additive manufacturing, oil and gas, and so forth. Combining knowledge graph enhanced retrieval augmented generation systems, there's also use cases from hydraulics with an existing Q&A system and work for operations management. And basically, we would place our work here in this kind of intersection in between really focus on maintenance and assembly assistance in the hydraulics domain using knowledge graph enhanced rack systems. Now, with this, let's move on towards the contribution. And here we develop a framework that fulfills mainly these three following requirements. So first of all, of course, we want to have a natural language input. And this natural language input shall be used to search for a specific step in an existence maintenance instruction. The second requirement would be that we want to have a structured knowledge base in order to really achieve this deterministically forward going towards the searches of the next steps. And the third requirement would be to generate again a natural language answer, which is presented back to the user. Now we compared, let's take a look first at the second requirement. So we call this the maintenance and assembly knowledge base. Here on the top left, you see a typical representation from a document of such an assembly instruction. And you can identify different elements. For instance, you have here the process label, different step description, and you see these kind of additional accompanying notes typically found. For instance, here it's about a environmental hazard notification, as well as accompanying information such as the images. Now, we build up a very small scale ontological model, simply linking the individual processes with different steps, sequentially chaining these steps, and through so-called data type properties, we attach the different description, additional notes, warning labels to each of these steps. So for 4 different scenarios, we instantiated, we formulated concrete instantiations of this class model. We implemented them as so-called simple RDF graphs, so resource description framework, which simply chains different objects in this graph together. And now we wanted to evaluate how to make this really usable for our large language model-based rack system. So as a very first, let's say the really simple, naive embedding approach, we just simply encoded mostly the step descriptions and label into one JSON file. And of course, for the more advanced rack system, that would be appropriately embedded into different vectors to automate the search for most appropriate steps. Now, as mentioned, we did it for 4 example scenarios of a hydraulic test bed. I'll get to the concrete numbers of how many tests we had in a minute. Now, we compared 4 different retrieval architectures and workflow in this work. And mainly, I already mentioned the, let's say, really naive approach to dump this sort of knowledge base together with the user query into one prompt, feed it to a large language model, and hope we get the correct identified step as an output. Now, the second architecture is, let's say, the classical rack approach. So we first search with the user input against the different step description and obtain 3 results, of which we, let's say, assume the first one to be the one that is further used in the pipeline. And to enhance on this, the top 3 research of the simple rack architecture are again compared and re-ranked by another large language model to eventually improve upon the decisions. And we wanted to know, for this concrete use case in this scenario, is there actually really a performance increase in using these more involved architectures? So let's dive a little bit into detail on this framework. So again, here in the middle, we see our knowledge base. So basically all the structured knowledge of the assembly instruction. We have a knowledge base retriever, which operates on so-called Sparkle templates. So Sparkle is just a specific query language to easily access such RDF graphs. So this is really, let's say, deterministic. We know exactly what kind of results we would expect given a specific query. So our plain LLM approach goes, uses a prompt template, and as mentioned, uses this JSON file of the entire knowledge base. We have the classical plain rec pipeline, which branches also over to this re-ranking. And once we retrieve this step, we generate the natural language-based answer. This was our third requirement, which is presented back to the user. Now, let's go a little bit into the evaluation of our results. And here, notably, we distinguish between two query types. We have explicit and implicit queries. The explicit one really use and restate key terms from the step description, whereas the implicit ones are more ambiguous wording. Let's make a concrete example. So assume the step description is remove the protective cover of the oil filler neck of the compact pump. So the explicit query really would reuse these words like protected cover and oil filler neck, whereas the implicit query would simply say the little cap over the filler stub is gone. Now with that, let's look at some results. So we generated 5 implicit and 5 explicit queries for each step of 4 scenarios. So in total, we analyzed 230 natural language queries. And as you can see on the average recall results, so whether the correct step, the step that was intended by the user to find, was really the first results at the end of our pipeline. Here on the x-axis, you can see the 3 different retrieval architectures. And indeed, we could measure some sort of performance increase here overall averaged on all these queries. However, if we look at some concrete scenarios, the results look a little bit different. And in fact, for the explicit queries in this hydraulic bleeding scenario, the re-ranking does not improve the performance. On the contrary, it even decreases a little bit the performance. However, especially for this implicit formulation of queries, there was a continuous significant improve through the re-ranking. Now let's look at the variance a little bit inside the steps. So we further go into the details of the results, and there's some notable variance in between the steps, of course, raising the question whether what is actually good formulation of a maintenance instruction and a bad one. And there are some outliers, but generally the implicit formulations are a little bit harder and deliver slightly worse results. I'm not going to go much into detail here. We developed a simple graphical user interface just to really motivate and ease a little bit the evaluation through industry experts. But this will actually be also stated more or less for the outlook. So, of course, some notable limitations must be acknowledged here. So first of all, of course, the step-level isolation is a kind of hard assumption. The real-world operations might be a little bit more dynamic and less focused on really describing what my past actions and steps were. Similarly, right now, as we've seen in the second results, at the moment, the re-ranking is kind of the last authority in our pipeline, which might be a little bit over-reliance on this LLM-based re-ranking. We only looked at sequential workflow so far, so there's little branching or loops, and there's a still limited scope of the evaluation. So first of all, whether the information is actually used, we'll need to analyze this more quantitatively. And also we would like to gain now with the user interface improved industrial user feedback and scale the system also towards larger instructions. So with that, I'm at the end of my presentation. Thank you all for your attention and happy to answer any questions.
Hello. Am I audible?
Yes.
Okay. So it was a great presentation, Joshua. I
Thank
just
you.
want to know one thing. What are your future plans now?
So the future plans, especially is we with this company where we got the test beds here at our lab, but also with the other companies, we want to make a little workshop to really find out what is actually now a little bit more get a feeling what would be a natural way of using them. This is such a system in a real world scenario, and thereby also identify our optimization goals. Let's say I think there we have different projects, and it's also the question now, okay, does it really we have a good score for, let's say, a certain recall now. Do we go now and optimize this, or do we want to enhance precision and so on? So there are many possible design objectives, and we need to get a better understanding for the actual user towards which parameter we need to optimize and do further research. This would be the next step.
Thank you. Over to the other chair. Do you have any question? Professor Noora.
Yeah, I have one question. Thank you so much for this wonderful presentation. My question here is that how does your system manage uncertainty when user queries are incomplete? Like user asks something that is incomplete, how can the system respond to this kind of incomplete queries?
Yeah, that's a very, very good question, which is also, of course, quite hard to assess. So we hoped to mimic this a little bit with this implicit formulation, and there is no, or let's say we wanted to assess whether a large language model through the semantic understanding can intrinsically handle this incompleteness, fill it eventually, and still, especially through the re-ranking mechanism, deliver a correct answer. But I think you're correct in that sense that it is some sort of evaluation metric of what even would be a valid user input, or to have sort of a gate to really handle completely, let's say, nonsensical inputs would still need to be added, probably.
Thank you so much.
Thank you.
Thank you. Our next presentation for today is by Satoko Itaya, who will be presenting Risk Priority Index for Cross-System Deadline Protection of Wireless Mobiles in Smart Factory. You may now begin your presentation.
Thank you for introduction. So I will share my presentation. So can you hear me?
Yes, we can.
Thank you. And okay. So good morning, everybody. And I'm actually I'm not in the morning now, and in Japan it's night. I'm working 12 hours yet, so I'm a little bit tired. So I'm sorry about if my English is not so good. So today I would like to introduce a little bit for myself. So I'm working with stable wireless communication in the factory with users in the real factory for the actual production lines with users 10 years. So my work is based on the user's needs. So today I will report some basic research on the risk priority index for cross-system deadline protection of wireless mobiles in smart factories. And at first, I would like to explain for the wireless AGV in smart factory. So AGV is automatic guided vehicle. Maybe everybody knows, or some people knows for that. So managed via wireless networks are used to transport parts and products in smart factory. This is the figure is a typical AGV in the car manufacturing factory. And actually for this white one is wireless antennas. And this mobile base is can carry the containers with various parts, and sometimes the car itself car body itself. So then factories are complex environment as mentioned for the last presenter. And also the managing HV is also a complex problem. And the transport delay is occurs due to the queuing of HV traffic and blocking of the radio signals. Transport delay is a critical point, can have large-scale impact of production line. And managing AGV delay is the multi-system issues involving production system and AGV transport system and wireless network system. And this is the basic view of wireless AGV operation system. So production manager here, AGV controller here, and wireless LAN controller here. And for the access point to the communicate with AGV is connected with the backbone network. And the AGV communicate with the AGV controller via wireless access point. And first, the production manager send the transport request to AGV controller, and afterwards the AGV controller sends the navigation and navigation commands to the AGV. And next slide, I will try to explain for the our proposal way. And the AGV trip schedule is shared between the AGV controller and the production manager. And we can draw this like the AGV trip scheduled for the diagram. And the AGV move from departure position to the destination position via several points. This is just simplified for this 3 point. We don't need to do the only 3 point. It's more, we can put several points, of course. The time is down for the this direction. And the schedule arrival time is destination is here. But we can set up for the application side for the critical deadline. If we cannot receive this signal until here, it's a problem. So because of that, we can set up for the risk threshold here, limited for the safe delay. And related to that, we can set up for the risk threshold for the previous. So we will keep this point anyway, so we can be the handle for the production line is not stopping for the AGV. And the fact is happen if the problem is available. So this is the why we need for this kind of management is showing for the same figures. So AGV tip progress is shared between, again, for the AGV controller and the production manager. And consider something happen here. And the schedule delay is here. However, for this delay event is happen, so the beer point, this AGV is not coming this time and delayed this time. So this case, so beer point, we can expect this is getting over for the risk threshold. So we need something protection action to reduce the delay to decrease for the delay to final delay for before to reach for the risk threshold. Then now I'm introduced for the, I'm briefly explain the idea for the risk priority index RPI. And usually there is more than one AGV. So we need a way to compare the priority of the protective actions for all AGVs. So we propose to use the risk priority index for that. And RPI is defined as the rank of AGV delay risk. That is the AGV with a high risk compared to other AGVs has high RPI, sorry. Then in general, risk is defined based on the probability of delay and the cost of delay. In the special case of AGV, transport for assembly line, the cost is typically a binary value 1, delay x, this is delay, deadline, delay exceeds the deadline, and the 0 is doesn't. So this case, the risk is just the probability of delay exceeds the deadline. And now I would like to explain our proposal for the product protection action in the wireless AGV operation system. The AGV controller report to the progress of the schedule. Then the production manager decide RPI for all AGVs, what is delay or on schedule or early or something like that. Then they are informing the AGV controller and for the wireless controller too. So whether the cause of the delay, the protective action should aim to prevent all types of possible future delay. So there are many possibilities available, but we would like to concentrate on the focus on the protection of quality of wireless communication. The wireless LAN controller now use the RPI, then to allocate access point resource to AGVs. The wireless LAN controller can allow the priority AGV to execute early handover to the best access point with the best quality communication. Now I will show you for some testing simulation view, and actually this is a full view for the large factories, and this is a part of simulation. And this simulation has 3D model of the factories with the walls and the machineries and the pillars and the access point with pillars. And AGV moves along the path, this path, and connect with one of the many access points that it can detect at each point along the path. First, we'll show the typical access point handover behavior in the simulation factory. These plots, both plots, is a typical example of the change of the maximum data rate that an AGV can achieve as it moves along the path, switching from the access point. Left side is the normal handover and the standard mode, and the right side is priority mode, what we propose for the using for RPI. And in the standard mode handover, the rate drops as getting far away from the first access point, and changing to the access point again getting increased, and afterwards getting far away, then decrease the rate, and again such kind of fluctuate is coming. And this rate is jump up and drop up, drop down is continuously to continue, continuously always happen. But priority mode is the early handover to use for the best performance. So because of that, the AGV can keep for higher data rate. So this kind of things is very important. For example, for the first presenter mentioned, like for the using to make something, gathering information for the areas and to sending some servers, and we was checking from the virtual side or such kind of things. We need some special rate, so we should keep the rate is better. And this is the video example for the our simulation. And focus on the AGVs. Please focus on the AGV. The magenta is the magenta color based.
Excuse me, I'm sorry to interrupt. You have about a minute left.
Okay. So here is the delay point. And if magenta is stopping, but they can get a more early access point. Then this is the total simulation result, and the x-axis is the AGV's numbers, and the y-axis is the delay time. And here is deadline, and standard handover is getting increased number of AGV is over the deadline. But if we use such kind of method, we can achieve for the always to the under deadline. So the conclusion is this way. So we would like to use such kind of work. We are thinking to introduce should introduce such kind of things to the real world, and we want to continue to this work. And this is the acknowledgement. Thank you very much.
Okay, very nicely presented. Can you hear me?
Yeah, sure. Sorry.
Yeah. So what were the challenges you faced while working on this project?
Phase means what kind of phase you mentioned?
What were the real-time challenges?
Real-time challenges. Okay. So actually, we don't need to do under 1 millisecond or something like that. We achieved to the under 100 milliseconds is enough currently. So this is for the enough real time in this project.
Okay, thank you.
Yeah.
Can I?
Okay. Anybody? Yeah. So
Yeah, Dr. Noora wants to ask something.
Yeah, I want to ask, but I see Ginandi want to ask. Allow Ginandi ask. Mr. Ginandi, you have
Yeah.
question?
Yes.
Okay.
How you can determine the risk priority? Is it statistic or you have it from your simulation?
actually, it's currently only for the simulation, but it's possible for the at least the maximum delay we can decide. Maximum delays we can calculate, and also for the probability we can calculate also average also possible. So this is the depend on the factory how to implement. So we can do somehow. So but yeah.
Okay, understand.
Okay, thank you so much for the presentation. I don't have question for this. Thank you so much.
Thank you.
Thank you. Our next presentation for today is by Amir Ahmadi, who will be presenting soft fault estimation and localization in Y-shaped networks using OFDM-based signals. You may now begin.
Good morning, everyone. Can you hear me?
Yes, we can.
I'm just sharing the screen. Okay, is it clear, my presentation?
Yes, we can see.
Okay. I would like to thank the session chair and the conference organizers for the opportunity to present today. My name is Amir Ahmadi, a PhD student at the University of Lille, and I would like to present our work on soft fault estimation and localization in Y-shaped networks using OFDM-based signals. This work is a collaboration between the Institute of Electronics, Microelectronics and Nanotechnology and the Research Center in Computer Science, Signal Processing and Automatic Control in Lille, France. The main objective is to develop an online monitoring system capable of locating, estimating soft faults in wired networks. In this presentation, I will introduce the context of the network and our objectives. Then, I will briefly review the diagnostic methods used. After that, I will present the transformatory-based approach using OFDM-based signals along with the experimental study. Finally, I will conclude and present future research directions. Wired networks are the main component of network control system, capable of connecting sensors, controllers, actuators, and they are responsible for energy and data transfer. Modern systems such as electric vehicles, autonomous system, and industrial automation rely heavily on network control system. Therefore, continuous monitoring of the cable health is critical for safety and performance. Wired networks are exposed to faults. Faults are generally can be categorized into two categories, a hard fault and a soft fault. A hard fault, like an open or a short circuit, where the energy and data are totally interrupted and we have a system failure, while soft faults are a partial degradation in the cable that does not affect the data and the energy transfer, and the system remains operating. Our objective is to design an online monitoring system for communication networks using orthogonal frequency division multiplexing signals capable of detecting the soft fault, locating its position, and estimating its severity. Two main online diagnostic approach, the reflectometry and the transfermetry-based methods. To start with the principle of reflectometry is where we inject a signal from an emitter and a receiver due to the presence of a fault in the network where we have impedance discontinuity. Part of the injected signal will be reflected back to the emitter, and the analysis of the reflected signal at the emitter is what's called by the principle of reflectometry. While the transfermetry-based method is where to make the analysis of the received signal at the receiver. And here we define the transmission coefficient, which is the received signal over the emitted one. In this work, we used OFDM pilot signal to estimate the channel transmission coefficient using a transfermetry-based method. This channel coefficient is estimated by averaging the ratio of the received pilots to the transmitted one. This method provides robust estimation even under noisy conditions. The experimental validation is performed on a test bench, as you can see to the left, where we have a test bench network using unshielded twisted pair cables. The characteristics of these cables have an impedance of 120 ohm. We are working on a frequency bandwidth up to 250 megahertz. We can sample this topology by the figure to the right, where we see a Y-shaped network. The fault can be presented in red, as we see in the figure, from a distance x from the node. To estimate the fault severity, we define a ratio between the faulty and the healthy transmission coefficients. From this ratio, the fault impedance can be estimated using the following equation, where ZC is known by the characteristic impedance of the cable, and the ratio R is estimated from the transmission coefficients. The following results show the transferogram in distance domain. We can see the difference between a reference or a healthy TC in a healthy situation and the estimated in real time, the estimated TC. We can compute the ratio that we defined, and then we can estimate the fault severity. In practical case, where we inserted a series resistive fault of 5 ohm, we obtained the estimated severity up to 6.6 ohm. And therefore, we are able to estimate even very small soft fault in the networks. In order to localize the position of this soft fault, we define a residual function, which is the difference between a healthy situation or a reference TC and an estimated TC from the peak in distance domain of this residual function, where in order to define the estimated position x of the soft fault in the network, we can see to the right the obtained residual function in distance domain from the peak obtained at the distance 23.7 meters. We are able to estimate the exact position of the fault, where the exact position in the real network is 5.17, and we obtain it from the signals by 5.09 meter. This demonstrates good estimation accuracy. Now, to characterize the fault, transmission coefficients are estimated under varying noise level using simulated OFDM communication chain. In this model, the received signal is expressed as the transmitted signal Y multiplied by the channel transmission coefficient H plus an additive noise term. The transmission coefficient is estimated using pilot signals transmitted on each OFDM subcarriers. This allows to reconstruct the channel response and apply the transformatory-based diagnosis method directly using communication signal without adding any hardware in the network. In the following slide, the plot diagram represents the complete OFDM communication chain used for the fault diagnosis process. An additive Gaussian noise is introduced at the receiver with SNR values ranging from minus 20 dB to 30 dB in order to evaluate the robustness of this approach. The simulated fault characteristics are fixed with a fault position of 5.17 meter from the node and a fault impedance of 5 ohm, which is considered a very soft fault, a very low fault that does not affect the data and the energy transfer. As a result, we can see that both the fault impedance ZF estimated and the fault position X can be accurately estimated over a wide range of SNR values. In particular, when the SNR is greater than 0 dB, the method provides high accuracy in both the fault severity estimation and fault localization. This confirms that the transformatory-based method combined with OFDM signals is robust to realistic communication noise level. To conclude, we have proposed the design of an online monitoring system based on transformatory diagnosis method using OFDM communication signal. The method is studied on a Y-shaped network. The proposed approach enables the estimation and localization of the soft fault in the network. Both experimental and simulation result confirms the robustness of the method under varying noise levels. For future work, several research directions are planned. First, we aim to generalize the method to a more complex communication topologies, such as the bus network, and we will extend the fault model to include various variations in inductance, capacitance, and conductance of the characteristic of the cable, and not only rely on resistive fault. Finally, we'll investigate the complementarity between the reflectometry-based method and transformatory-based method in order to improve global diagnostic performance. Thank you for your attention. I'll be happy to answer your questions.
Thank you. Very well presented. I have no questions as such.
Thank you. Thanks so much.
Dr. Noora, you would be having some questions.
I'm ready to hear your answers.
Yeah, can this approach be applied to wireless network or is only for wired network?
This method can be applied to more complex network topologies. This method is based on time domain analysis. We have already worked on a frequency domain for complex network and already published. This method is to localize the position of the fault. For complex network, we were able to identify the faulty branch in the network, even in a very complex network topologies. We are dealing with autonomous electric vehicles, so we don't have a very complex topology. Most of the topologies depends on a bus network and Y-shaped networks. And the objective is to estimate soft faults that is hard, it is very hard to be detected because they don't have any effect on the data and energy transfer. By the time they can be evolved into a hard fault and we can have a system failure.
Mr. Jinan, do you have question?
My name is Lukyanov. Excuse me,
Okay.
Professor Lukyanov. Okay.
Okay.
Thank you. Doesn't diffraction bother you?
Sorry, can you repeat your answer, your question, please?
Doesn't diffraction bother you? Diffraction.
The diffraction in what?
Optical diffraction. Yeah.
If you mean by diffraction the attenuation that could happen or the
Yeah.
noise, and the noise in the network, we can see in the slides. I don't know if you can see
Yeah.
it in the slides. In this case, we have it in a practical case, we have it in a real case. In this method we rely on the peak obtained by the residual, but also we have attenuation. The problem or the complexity is because of the attenuation that appear due to the noise, due to the cables, due to even could be from the junctions or any from the sensors. But from this method, we were able to localize and to estimate the severity of the fault even with a real measurements on a test bench.
What is wavelength? Wavelength.
Can you repeat, please, your question?
What is wavelength?
The wavelength. Okay, the
Yeah.
wavelength. The wavelength. Here we have it. Since we are working on a frequency bandwidth up to 250 megahertz, if we consider that due to this,
Enough. It is enough. It is enough. Thank you.
Okay. But in order to be, we have just to be more precise in the localization of the fault, we have a decision in distance up to 60 centimeter. So if we can localize the fault at 5.09 while the actual one.
I see. Thank you.
Yes.
Thank
Okay.
you. I see.
Thank you for your question.
Thank you.
Thanks so much.
Our next and last presentation for today is by Nikolai Skutz, who will be presenting synthetic data generation for visual geolocalization using GTA-5. You may now begin.
Thank you very much. I hope you can all see the slides. Today I want to give you a brief overview of our work on synthetic data generation for visual geolocalization using the video game GTA 5. And first of all, I want to demonstrate why visual geolocalization is important, especially for automobile augmented reality applications. Here you can see an example of an application that visualizes wind turbines where they are planned to be built. And this requires a precise estimation of devices' position and orientation to correctly visualize the wind turbine as on the left image. The problem is that the accuracy of device sensors such as GPS and compass are insufficient for this use case and often result in visualizations like in the center or on the right. By using visual data, the localization accuracy can be improved significantly, which is then called visual geolocalization. There are three main types of visual geolocalization, which are mainly distinguished by the data they used. The same view approaches use these images from the same domain for query and reference, for example, ground view images, and then find matches between them to localize themselves. Cross-view approaches also aim to find matches, but query and reference images are from different domains, for example, ground view panoramas and aerial view images. And model-based approaches use georeferenced models as reference, which are either rendered or directly used to estimate the skyline. However, development and evaluation of new methods is limited by the data that's available. Existing data sets mainly consists of data for only one category of geolocalization approaches, which makes comparison between approaches very difficult. They lack ground truth data, such as the 6 degrees of freedom pose of the camera, which is crucial for RR, for augmented reality applications. The segmentations, the depth maps, or georeferenced models are also missing, and we lack data from rural non-mountainous environments. So we would like to address these limitations by creating a new data set for visual geolocalization. However, generating data is especially annotating the data is very expensive, and that is why we propose to generate synthetic data from the video game GTA 5. And the advantage of the video game GTA 5 is that compared to other games, it offers an extensive, rich, and highly realistic world, detailed light and physics simulations, and autonomous motion of NPCs and vehicles. Furthermore, synthetic data generation has many advantages, including the inexpensive and efficient data acquisition compared to real-world data, full control over environment and camera parameters, automatic export of metadata and camera parameters, and the automatic generation of ground truth segmentations and depth maps. In order to generate all the data necessary, we developed a pipeline consisting of these 4 main steps. First, the locations at which the data should be generated are selected. This can either be done randomly or manually using a web application. And then for each of the selected locations, data is generated, which is described in the following steps. First of all, the game modification, where the player model is teleported to the desired location, the weather and the time of the days are set, the player model and the HUD elements are hidden and the scene is frozen, and a new camera with the desired parameters is created. After that, the image and metadata can be generated and exported. And finally, if panoramas are generated, the rendered cube maps are then stitched and blended. So I will go into a little more detail for these steps now. First of all, if the locations are not selected randomly but manually, they can be selected using a leaflet-based web application we developed. This application allows to switch between 3 different map representations, place and modify markers, as well as import and export the position and orientation of the markers. After the rendering locations are selected, the following steps are executed at each of the locations. First, the tool scripthook-v or scripthook-5 is used to inject custom code into the game, which allows us to modify all game parameters. Here in this example, you can see a screenshot from the game as it usually looks like, and then we can adjust time of the day, weather, hide all the UI elements, and adjust the camera to get the result like on the right side, which we can then use as data. After setting up the scene and the camera, the custom script is then used to export the metadata and the camera parameters. After that, the graphics debugging tool RenderDoc is used to capture the frame. This tool intercepts the rendering pipeline and allows us to export intermediate results like the undistorted RGB image, depth buffer, and stencil buffer. Depending on the data generation mode, multiple captures can be taken. So for example, if I want to generate a ground view panorama, I can generate 6 different views at the same location where only the camera is rotated. If I want to create drone view images, the camera is rotated around the building or the location to create multiple views. Or if I want to create satellite view images, the camera is positioned above the location and then pointed downwards. Here's an example for the intermediate results. We can export directly from the rendering pipeline. On the left, you can see an undistorted RGB image. In the middle, you can see the stencil map, which can then be used to create a ground truth segmentation. And on the right side, you can see the depth map. Finally, the data is then post-processed. So if I want to create panoramas, 6 cube maps are captured and then finally stitched together. That works really well for the depth and stencil buffer, but it doesn't work very well on the RGB images because of the lighting. That creates visible borders at the stitching borders of the panorama, which you can see on the right. Our solution to that is capturing more cube maps in between, so in total 18, and apply blending between these cube maps during the stitching. This pipeline, which I just introduced, has then been employed to generate the following dataset, which consists of all the data necessary to develop and evaluate and also compare different types of geolocalization approaches. We generated ground view data for a total of 3,000 locations, 1,500 in rural and 1,500 in urban settings, and their corresponding satellite view images, as well as the metadata and the camera parameters. We also created drone view images at 450 locations with 64 images each, and also the corresponding satellite view images and metadata. To evaluate if the synthetic data is then applicable to real-world problems, we implemented the state-of-the-art cross-view geolocalization approach named Sample4Geo to evaluate our approach and to overcome the domain gap between the video game and the real world. This approach was jointly trained on synthetic and real world data. For that, we used only 70% of the original real world data. As you can see in this table, if the approach was trained and evaluated on synthetic data, it scores nearly perfectly. But if it's trained on synthetic data without seeing real-world data and then evaluated on real-world data, you can clearly see the impact of the domain gap. If the approach is jointly trained on synthetic and real-world data, though, the domain gap could be successfully bridged. So the key results can be summarized as follows. Synthetic data from GTA 5 can be used to train visual geolocalization approaches, and the domain gap is there, so the domain adaptation is necessary to overcome this gap. Future research on this topic may focus on one of the following 3 areas. First of all, enhancing the realism of the data by incorporation of modifications which add more realistic textures, lighting, or weather simulations, or transition to a new version, the GTA 5 Enhanced Edition, which offers enhanced graphics and supports ray tracing. Second, one could enhance the diversity of the data, for example, by changing the environmental parameters, such as the weather or the time of the day. We could capture image data during the rain or during the night, and generating new data, which can be semantic segmentations for other visual tasks or digital surface models for model-based visual geolocalization approaches. For further information, please refer to our paper, write me an email, or check out the Git repository by scanning the QR code. Thank you.
Okay, it was a great presentation. I have one quick question. Why did you select leaflet-based web application?
I selected it because it's an easy open source web application which allows me to load custom maps. So not only real maps like from Google Maps or something, so I could load the game map tiles at different detail levels and then could easily export the location and orientation which I use to create the data at that locations.
Did you try some other alternative too?
I did not try another tool because that fulfilled all my requirements and was fairly easy to use.
Okay, thank you.
Thank you so much for this wonderful presentation. I have only one question. Can you hear me, please?
Pardon?
Can you hear me?
Yes.
How well does your synthetic data that you generated generalize to real-world environment? How well?
How well to what environment?
Real-world environment.
I can go back to the slides. So it does work in real-world environments. So you can see this one, the third one is trained on synthetic and real-world data, but used less real-world data. So it can be used, but as you can see on the in the second row, only training on synthetic data without applying domain adaptation leads to worse results. So you need some kind of domain adaptation, which can be training with both data or applying another neural network that converts from one domain to another domain.
Okay, I understand. Thank you.
Thank you, Nikolai. We'll now move towards the closing remarks. I sincerely thank our authors for their excellent presentations and contributions in this session, and all our participants for being a part of this international conference. I hope this session was informative for everyone, and on behalf of the whole team, I thank you for your support during this 11th version and all the previous 10 versions of the conference. We will be happy to have you in the 12th version in 2027. All the presenters will be getting their digital certificates within 2 working days via email. The publication will be live within 7 to 8 months. Kindly cooperate with the team of ICICT 2026. I would also like to thank our session chairs. I would like to thank Dr. Anubha Jain and Nura Muhammad Sani for chairing this session, and here are our token of appreciation for them. On behalf of Team ICICT and Global Knowledge Research Foundation and partners, we thank you so much. Just before we end our session today, I would like to request everyone to please turn on their cameras so that we can take a virtual snapshot. All right. 1 second. Okay. Thank you so much, everybody.
Thank you. Thank you, everybody. All the best for your future research. Thank you.
Thank you. The session is now adjourned. Stay safe and take care.